Good morning, students. Today we are going to discuss about alkynes. This is a subtopic of our second topic, acyclic hydrocarbons, in second unit, that is organic chemistry. So, in the organic chemistry, our first topic is structural theory in organic chemistry, and second one is acyclic hydrocarbons. In acyclic hydrocarbons, we have already discussed alkenes, and now we are going to discuss about alkynes. Okay, right. Now, what are alkynes? Let us see. Alkynes are unsaturated hydrocarbons. Unsaturated hydrocarbons which contain carbon-carbon triple bond. So, unsaturated hydrocarbons which contain carbon-carbon triple bonds are called alkynes. So, what are unsaturated hydrocarbons? Unsaturated hydrocarbons are nothing but the hydrocarbons which contain carbon-carbon multiple bonds. That is either carbon-carbon double bond or carbon-carbon triple bond. They are called unsaturated hydrocarbons. And in unsaturated hydrocarbons, we come across alkenes as well as alkynes. So, alkynes are the unsaturated hydrocarbons which contain carbon-carbon triple bonds. These alkynes are also called acetylenes because they are the derivatives of acetylene. Acetylene is the simplest alkyne or the first member of alkyne series. As the rest of the alkynes are all derivatives of acetylene, their alkynes are also called acetylenes. So the general formula of the alkynes is CnH2n minus 2. This one. CnH2n minus 2, where n is an integer. And the triple bond is known as acetylenic bond. The triple bond present in alkynes is called acetylenic bond. And many alkynes are found in nature and they play a special role in organic synthesis. So, most of the alkynes, they are available in nature and they are the starting materials for most of the organic compounds. So, this is the importance about the alkynes are acetylenes. Next. The simplest member of alkyne is acetylene visit, and this one, the general formula we have already discussed, CnH2n minus 2, where n is equal to 2, then we will get this formula, CnH2n minus 2. N is equal to 2, then we get C2H2. This is the starting member or the first member of alkyne series. This is only called acetylene. So in acetylene, carbon atoms share three pairs of electrons. Carbon atoms share three pairs of electrons, thus a triple bond is formed in between the two carbon atoms. Triple bond is formed in between the two carbon atoms. Due to sp hybridization of both the carbon atoms in the carbon atom, a triple bond especially. In alkynes or in acetylene, these alkynes or acetylenes are linear in shape because of sp hybridization of carbon atom, and the bond angle in the molecule is 180 degrees. Here, each carbon is sp hybridized, and there is one sigma and two pi bonds in between two carbons. The triple bond is present. This triple bond is made up of one sigma bond and two pi bonds. Triple bond is made up of one sigma and two pi bonds. So there is one sigma and two pi bonds between the carbons. The pi electron cloud makes a single cylindrical sheath above the line joining the carbon nuclei. So here pi electron cloud is present along the internuclear axis of the two carbon atoms. Thus, the molecule it is linear in shape due to sp hybridization. The bond angle is 180 degrees. This one you can observe cylindrical sheath of pi electron cloud of both the carbon atoms. Due to the presence of three covalent bonds, that is a triple bond, that is three covalent bonds or triple covalent bonds in alkyne. See double bond C bonding, which is more stronger, when compared to C double bond C. C triple bond C is more stronger when compared to C double bond C, and which is more stronger than C single bonds. C single bond C is present in alkanes. C double bond C is present in alkenes, and whereas C triple bond C is present in alkynes. So alkynes contain C triple bond C, which is a strong bond. Which is a strong bond. Okay. Now let us see the preparations of alkynes. How these alkynes or acetylenes are prepared like this. A carbon-carbon triple bond is formed in the same way as carbon-carbon double bond. So in carbon-carbon double bond, how it is formed? Due to the elimination reaction of alkyl halides or alcohols or dihalides, etc. So here also carbon-carbon triple bond is formed in the same way as the carbon-carbon double bond, that is elimination of atoms or groups from two adjacent carbons. It gives the alkynes or acetylenes. Here you can see the general example. General example, here let us consider. Here adjacent carbon atoms, different groups are present, AB and XY. So this carbon has A and X, and this carbon has B and Y groups. Now in the first step, what happens? Loss of AB takes place. So two sigma bonds are broken and a new pi bond is formed. This is elimination. Okay. Then in the next step, what happens? These two sigma bonds, that is these two sigma bonds are broken. Another pi step, next step, what happens? Two sigma bonds are broken here and here, and a new pi bond is formed in between the two carbon atoms. Thus, an alkyne is produced. So, alkyne is obtained by the elimination reaction. Elimination reaction. So, here four atoms or groups are eliminated to give two pi bonds. Two new pi bonds are formed. Now, let us see the specific example of specific method to prepare alkynes. The first one is dehydrohalogenation of vicinal dihalides. Dehydrohalogenation of vicinal dihalides. So what is meant by dehydrohalogenation? D means loss. What are all lost? Hydrogen and halogen. So hydrogen and halogen. So dehydrohalogenation means loss of removal of hydrogen and halogen from adjacent carbon atoms of a vicinal dihalide. Then what is vicinal dihalide we said? Vicinal dihalides are nothing but the dihalides in which two halogen atoms are present on adjacent carbon atoms. When the two halogen atoms are present on the same carbon atom, it is known as geminal dihalides. Here we are considering vicinal dihalides, where the two halogen atoms are present on the adjacent carbon atoms. So, in this method, this is a method which is a very common method of preparation of alkynes. The preparation involves formation of alkene followed by formation of alkyne. So, removal of first two atoms produces an alkene. Removal of the next two atoms or groups, it produces an alkyne. So, vicinal dihalides are treated with alcoholic KOH. What is it? Alcoholic KOH is the reagent which is used for the dehydrohalogenation. So, this is called dehydrohalogenating agent, alcoholic KOH. That is KOH in presence of alcohol. Uh, so, vicinal dihalides are treated with alcoholic KOH followed by sodamide in liquid ammonia. Sodamide is sodium amide in liquid ammonia. So, then what happens? Dehydrohalogenation takes place, and this involves loss of HX in two steps. Loss of HX. H is hydrogen, X is halogen. So, dehydrohalogenation in two steps takes place to form finally the alkyne. So initially we will get alkene, then in the next step we get alkyne. So let's see the dehydrohalogenation reaction with an example. This is general example, a general molecule we considered. So this is this carbon, it has one hydrogen and one halogen atom, and the adjacent carbonate also has one hydrogen and one halogen atom. Okay, now in the first step, what happens when this vicinal dihalide is treated? Dihalide, vicinal means adjacent carbon atoms, they have halogen atoms. When this vicinal dihalide is treated with alcoholic KOH, this is a fast step. Then what happens? Hydrogen from one carbon and halogen from another carbon are removed. H from one carbon, halogen from another carbon are removed. Then what happens? We will get an alkene. An alkene is produced here. Okay. Now in the next step, what happens with this alkene? It reacts with sodium amide. Sodium amide in liquid ammonia. Sodium amide, this is NaNH2, sodium amide in liquid ammonia, which is a slow reaction. Then what happens? This H and this X are also removed. To form an alkyne. You can see here C triple bond C alkyne, C double bond C alkene, C single bond C alkene. Alkane having two halogen atoms adjacent on adjacent carbon atoms. Therefore, it is nothing but vicinal dihalide. Vicinal dihalide. Okay. So this is the method in which vicinal dihalide undergoes dehydrohalogenation in two steps to form finally an alkyne. In its first step, alkene is produced, and the second step, what happens? We will get an alkyne. Okay. Now let us see one specific example for the preparation of alkynes by dehydrohalogenation. So here let us consider this example. What is this? This is 1, 2, 3 carbons, therefore propane, and first carbon bromine, second carbon bromine. Therefore, it is 1, 2 dibromopropane. 1, comma 2, first carbon, second carbon. Di means 2, bromo means bromine atoms, propane as it is a 3 carbon alkane. So 1, 2 dibromopropane is a vicinal dihalide on adjacent carbon atoms. 2 halogen atoms are present, therefore it is a vicinal dihalide. Now it is subjected to dehydrohalogenation with alcoholic KOH. Then what happens? H from one carbon and Br from another carbon are lost. H from one carbon and Br from another carbon are lost. Then we will get this compound. So 1 bromopropene is obtained. The next step, this 1 bromopropene, it loses H from this carbon and Br from this carbon. H from this and Br from this adjacent carbon atoms, H and Br are lost. Then in presence of sodium amide in liquid ammonia, then we will get an alkyne. That is, here we started with 1,2-dibromopropane. Therefore, the final product produced is propyne 3 carbon alkyne. This is propyne. So, in the first step, we will get propene double bond. In the last step, that is in the second step, we will get the propyne, that is triple bond. Triple bond is present in between the two carbon atoms. That is nothing but an alkyne. This is nothing but an alkyne. Okay, so this is first preparation. That is dehydrohalogenation of vicinal dihalides. So vicinal dihalides, when they are subjected to dehydrohalogenation with alcoholic KOH followed by sodium amide in liquid ammonia, we get finally alkynes. So specific example we discussed here, that is 1,2-dibromopropane. When it is subjected to dehydrohalogenation with alcoholic KOH, initially in the first step we get 1 bromopropane, and this in the second step it combines with or it reacts with sodium amide in liquid ammonia to form propyne. So this is first method. Now let us see the second method of preparation of alkynes. This is dehalogenation of tetrahalides. What is that? Dehalogenation. D means loss. What is lost? Halogen atoms. Loss of halogen atoms of tetrahalides. So we should consider a tetrahalide. From the tetrahalide in the first step, two halogen atoms from adjacent carbons are lost. Then we get an alkene with the two halogen atoms, and in the next step what happens? The remaining two halogens from adjacent carbons are lost to produce finally an alkyne. So in this, the dehalogenating agent is zinc dust. Okay, zinc dust. So powdered zinc is used as a dehalogenating agent. So dehalogenation of tetrahalides minus of 2x2. So first step x2 removed, and in the second step another x2 molecule is removed. Then we will get an alkyne. So similar to alkenes preparation from vicinal dihalo compounds, the alkynes are prepared from 1,1,2,2 tetrahalo compounds. So 1,1,2,2 tetrahalo compounds. By treating with the alcoholic zinc dust, we will get finally an alkyne. We will get finally an alkyne. So here let's see tetrahalide. So an adjacent carbon atoms, each carbon has two halogen atoms. You can see here this carbon has two halogens, this carbon has two halogens. So altogether four halogen atoms are present and two adjacent carbon atoms. And when this compound, that is a tetrahalide, which is subjected to dehalogenation with alcoholic zinc dust, then what happens? This Zn, it takes this x2 and another x2, 2Zn, Znx2, Znx2. You can see here 2Znx2. So halogen atoms are removed by alcoholic zinc dust to form an alkyne. Alkyne C triple bonds, you can see it easily here. So an alkyne is produced. So this is a general example for the dehalogenation reaction of tetrahalides to form alkynes. Now let us see the specific example. See this specific example. Here 1 that is on first carbon, two bromines are there, therefore 1 comma 1, the number of the carbon is repeated. 2 on second carbon also two bromine atoms are there, therefore second carbon number is also repeated. So 1 comma 1 and 2 comma 2, 1 comma 1, 2 comma 2, tetra, because four bromines are there, bromo ethane. Why it is ethane? Only two carbon alkane it is, therefore it is ethane. So this is 1,1,2,2 tetrabromoethane. When this is treated with alcoholic zinc dust, the first step, this Zn, it removes two bromines. One bromine from this carbon, another bromine from this carbon is lost. The next step, what happens? This and zinc, it removes two more bromine atoms from this molecule to form finally acetylene. Acetylene, that is CH triple bond CH or C2H2, we can say. Okay, this is acetylene obtained. And other product is 2 moles of zinc bromide. 2 moles of zinc and Br2 here, Br2. Okay. So this is dehalogenation of tetrahalides to form alkynes. The specific example here we have considered 1,1,2,2 tetrabromoethane. When it is treated with alcoholic zinc dust, we get acetylene as a final product. Let's say the properties of alkynes. First of all, let us consider physical properties of alkynes. There one important property we have. Let's discuss about that. That the important property of physical property of alkynes is this acidity of alkynes. Acidity of alkynes. So, how do we explain the acidity of alkynes? Let's see. In alkynes, carbons are sp hybridized, which are more electronegative carbons than sp2 and sp3 hybridized carbons. As a result, the hydrogen attached to triple bonded carbon, that is in the case of terminal alkynes, the hydrogen atom which is attached to triply bonded carbons. In the case of terminal alkynes, we said because if it is a terminal alkyne, then only the triply bonded carbon will be having hydrogen. Otherwise, if the triple bond is present in between the chain, longest chain, then there won't be any hydrogen atom. Because of that reason only we said terminal alkyne. So when in the case of terminal alkyne only, triple bonded carbon will be having a hydrogen atom. Okay, so a hydrogen atom attached to a triply bonded carbon, that is terminal alkyne, it shows appreciable acidity. Appreciable acidity. So when compared to phenols and carboxylic acids, terminal alkynes are weak acids. Hence, they should be treated with strong base like Na and H2 or metals like sodium or potassium. Okay. So, as this alkynes, they are not strong acids like carboxylic acids or to some extent phenols, but they are weak acids. As they are weak acids, we should use a strong base like sodium amide or metals like sodium or potassium to remove that hydrogen from terminal alkyne. Okay, let's see. Example: acetylene. It reacts with sodium and liberates hydrogen gas, okay, to form the sodium acetylide. Let us see the reaction. This is acetylene. When it is treated with sodium metal in liquid ammonia, then what happens? This H hydrogen atom, H plus, it is removed from this acetylene. Because of that reason only we can say that acetylene acts as an acid. So this H is removed and it is replaced by sodium atom. Then we get sodium acetylide, which is a salt. Sodium acetylide salt is produced here. And in this reaction, if we consider 2 moles of acetylene molecule, one molecule of, or 1 mole of, let me say, 2 moles of acetylene, if we consider, here 1 mole of H2 gas will be released by replacing hydrogen atom from one of the hydrogen atoms from acetylene by sodium metal. So sodium acetylide is the salt produced when acetylene reacts with sodium metal in liquid ammonia, liberating hydrogen gas. So this is from this reaction we can say that as this molecule it is losing H plus, thus we can say that acetylene is acting as a weak acid. Now similarly, a strong base like sodamide, which also removes proton from terminal alkyne to produce alkylide or acetylide. Now, here another example we consider, that is same alkyne is same acetylene. When it is treated with another base like sodium amide or sodamide in liquid ammonia, then what happens? It also removes this H plus, and this removes H plus. Thus, we can say that acetylene, it is also acting as an acid in presence of a strong base like sodium amide. So, sodium acetylide is the product produced, and the other product is this NH2 and this H in the form of NH3. So, this is about acidic nature of acetylene. Now, here terminal alkynes are weaker acids than phenols and carboxylic acids. Those compounds are stronger acids than alkenes and alkenes. If we consider alkenes and alkenes, these alkynes are more acidic. And the acidic property of alkynes are quite useful in the synthesis of higher alkynes. So, with the help of this sodium or potassium acetylides, we can easily prepare higher alkynes starting from lower acetylides. Now, let us see the preparation of higher alkynes. Higher alkynes, how they are prepared from these acetylides. Let us discuss. Okay. Now, here, the acidic nature of alkynes can be used to convert small alkynes into big alkynes. Okay. So through carbon-carbon bond formation, new carbon-carbon bond will be formed, and we will get a alkyne with the longest carbon chain. And the acetylenic anions are Acetylidic, let me say. Acetylidic anions are powerful nucleophiles and can easily attack at electrophilic carbons of organic functional group. So, wherever an electrophilic carbon atom is present in a organic compound, then what happens? These acetylides, they go and attack that particular carbon to produce the longest carbon or a bigger alkyne, let me say. So, this is because of nucleophilic nature of acetylides. Let me see. And if a terminal alkyne is treated with a strong base like sodamide or metal, sodamide or a metal like sodium or potassium or organolithium, that is RLI. Organolithium, this is organic part, and lithium RLI, or organomagnesium halide, organolithium halide or organomagnesium halide RMGX. The lithium or magnesium acetylides are produced. Okay, lithium acetylide or magnesium acetylides are produced. These metal acetylides, they react with electrophilic carbon functions and produce higher alkynes. So these metal acetylides, they act as nucleophiles and they go and attack electrophilic carbon present in any functional group to form higher alkynes. Higher alkynes. That is alkynes containing more number of carbons, we mean to say. And thus, acetylene homologues are prepared by treating acetylides with an alkyl halide. So, homologue in the sense higher member of that alkyne series can be prepared with the help of acetylides when they are treated with alkyl halides to increase the carbon chain length. Okay, now let us see the example. Then we can easily understand what is that happening. So let's start with an acetylene here, treated with sodium in presence of liquid ammonia. Then we get sodium acetylide. The nucleophile is formed. Now this is treated with RX, alkyl halide. Then what happens? This Na and this X is lost in the form of NaX, is removed in the form of NaX. Then R, this this part of the sodium acetylide acts as a nucleophile and it goes and it acts or abstracts this R, that is alkyl group, to form higher alkyne. Higher alkyne. So here this alkyne is initially we started with acetylene having only two carbons. Now here we got an alkyne having more number of carbon atoms. It depends on the number of carbons present in this alkyl group. We will get the higher alkane. Higher alkyne. Okay, higher alkyne is produced. Now let us see the specific example here. With the RLI. Okay, RLA. This is with sodium and liquid ammonia. This is at the RLA. This, general example only because here we considered R. So let's see. C triple bond CH, that is a general alkyne treated with RLI. Then this H plus is replaced by Li. We will get this one, lithium alkylide. Okay, lithium alkylide treated plus RH. This R and this H, RH. The second step, what happens? This lithium alkylide, it reacts with another molecule of alkyl halide, like this alkyl halide here, RX. Okay. Then this is the nucleophile acetylide ion. It goes and abstracts this alkyl group from RX. Then we will get a higher alkyne, and this Li goes with X minus, Li plus with the X minus in the form of LiX. LiX. So here higher alkyne is obtained. Here another example we consider acetylene with the N-butyl lithium. RLI. R is N-butyl, that is normal butyl. Alkyl group here is butyl group. Okay, so N-butyl lithium, that is CH3, CH2, CH2, Li. CH3, CH2, 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 Li. This is N-butyl lithium. Then what happens? Mm, this acetylene, it combines with the n-butyl lithium, then this H plus is replaced by lithium, and we will get the lithium acetylide, and this is butane. N-butane is obtained here. Okay, so in the next step, what happens? Let's once produced, it combines with uh, alkyl halide. That is here we consider ethyl bromide. It goes and attacks this carbon atom. Thus, along that is high BR in the form of LIBR, and here we started with acetylene. Now here we got one, two, and in this beta, in between one and two carbon atoms, triple bond is present. Therefore, it is known as one butane. One butane. Okay. So here, like acetylides, with the help of acetylides. This is because of the another example here we consider started with CH3, CH2, C triple bond CH. That is, this is propine. This is one butane. We started with one butane. One, two, three, four carbons. One butane treated with n-butyl lithium. Then this H plus is replaced by Li. Okay. Then we will get CH3, CH2, C triple bond C Li. That is lithium, and this is butylide. Okay, lithium butylide ion. Okay, so this one. Now it combines with alkyl halide CH3Br here we considered. Then what happens? This ion nucleophile, it acts as a nucleophile, attacks this carbon to form a higher alkyne. We started with 4 carbon alkyne, and in this the finally we got 5 carbon alkyne. You see 1, 2, 3, 4 and 5. 5 carbon alkyne is produced. That is this pentyne, and in this pentyne 1 and 2 carbons, this is 2 3, in between 2 and 3 triple bond is present, therefore it is the 2 pentyne obtained in this reaction. Started with butane and produced by the reaction with n-butyl lithium followed by Rx, that is CH3Br. This is another example where higher alkynes are obtained from lower alkylides, and these alkylides are produced when the alkynes are sodium metal, okay, or potassium metal, etc. So this is about the acidity. So thus, the acidity of terminal alkynes permits its conversion into useful higher alkynes, and they have become an important building blocks in the organic synthesis. Okay, so this is about the preparation of higher alkynes due to acidity of alkynes, especially terminal alkynes, where the hydrogen atom can be easily replaced by metals like sodium, potassium, magnesium, lithium, etc. Okay. Now let us see the chemical reactivity of alkynes. Chemical reactivity of alkynes. So the chemical properties of alkynes are similar to alkenes, because in alkenes and alkynes, um, pi bonds are present. Okay, alkenes they have one pi bond, and alkynes they have two pi bonds. So similar to alkynes also undergo addition reactions. So like alkene, alkynes also undergo electrophilic addition reactions. So addition of halogens, addition of hydrogen halide, addition of water to alkynes is almost same as alkenes. So in all these additions, alkynes they undergo addition with two molecules of reagent, as they have two pi bonds for each carbon-carbon triple bond. So each carbon-carbon triple bond has three the bonds, Out of the three bonds, one is sigma bond and two are pi bonds. Because of the presence of two pi bonds, they undergo addition of two molecules of the reagent. Whereas in the case of alkenes, they undergo addition of one molecule of the reagent. Whereas here, two molecules, they get added over to carbon-carbon triple bond to give the final product. So this is about addition reactions. And here let us discuss one by one. Addition of halogen. So alkynes are less reactive than alkenes because of the strong C bond. C triple bond C bond is more stronger when compared to C double bond C, which is more stronger when compared to C single bond C. Therefore, alkynes are less reactive than alkenes in addition reactions of halogens. So the lesser reactivity is attributed to difficulty in the formation of cyclic intermediate. During the addition, cyclic intermediate is produced, and in the case of alkynes, there is a difficulty in the formation of cyclic intermediate. Because of that reason, they are less reactive when compared to alkenes. Here, let us discuss the addition of X2, that is halogen atom. Addition of X2, that is halogen, on alkyne C triple bond C. So when the X2 is added over to C triple bond C, then one X goes to this carbon, another X goes to this carbon, and two new sigma bonds are sigma bonds are formed with the two acetylenic carbons. Thus, here initially we get this compound in which one more pi bond is left behind. And this again undergoes addition with one more molecule of X2. Then what happens? These two atoms, they get added over to these two doubly bonded carbons and this pi bond breaks. Thus, we get the final product. Halogen atoms are present and two adjacent carbon atoms. Okay, if this alkyl group is there, we should not say 1, 1, 2, 2. It depends upon the number of carbons present in this alkyl group. We should number it. Okay, if this is H and this is H, we can say that it is 1, 1, 2, 2 tetrahedral compound. Okay, now let us consider the specific example here. Here we consider specific examples. So we started with 1, 2, 3, 3 carbon alkyne, that is propyne, treated with bromine. So bromine. Then what happens? This bromine, it forms a cyclic transition state which is unstable. You can see here one bromine atom, it goes and attacks this. Here a bond is formed in between this carbon and bromine. So this is a three-membered cyclic transition state is produced which is unstable, and one pi bond is broken. Two new pi sigma bonds are formed. This combines with another atom, that is from this Br2, one bromine atom is forming a bond here, that is one Br plus. The rest is Br minus, that will go and attack any one of these carbon atoms from the back side to form a dibromo compound. To form a dibromo compound, this one is produced, two bromine atoms. Okay. Then afterwards, it undergoes addition with one more mole of bromine to form. Here, this pi bond breaks and two new sigma bonds are formed. Two new sigma bonds are formed in between carbon and bromine. Carbon and bromine. Carbon and bromine. First step, this one, carbon and bromine. Second, here, due to attack of this Br minus from the rear side, one more bond is formed here, and the rest. Next step, another molecule of bromine, it goes and attacks this doubly bonded carbons. Thus, we get two more CBr bonds are produced. Thus, we will get a tetrahalo compound is obtained. So here we started with propyne. When two moles of bromine or two molecules of bromine, if we start with one molecule, two molecules of bromine atoms, bromine molecules, they get added. Br2, two molecules of bromine, they get added to C triple bond C to form finally 1, 1, 2, 2 tetrabromo propane 1, 2, 3. here. 3 carbons are there, propane. So first carbon 2 bromines, second carbon 2 bromine atoms. Thus it is 1122 tetrabromopropane is the final product obtained when propane is treated with bromine. Okay, this is halogenation with addition of halogen. Addition of halogen. So next one, addition of hydrogen halides. Addition of hydrogen halide, that is HX addition. HX addition. So in this reaction, what happens? Let's addition of hydrogen halide. The alkynes, they undergo electrophilic addition with HX similar to alkenes to form alkynyl halides. So, in alkenes also they undergo addition with HX to form alkyl halides, whereas alkynes they undergo electrophilic addition with HX to form alkynyl halides. Alkynyl halides. Now, the mechanism involves initial attack of here. Initial attack of hydrogen electrophile to produce vinyl cation intermediate. This one, vinyl cation intermediate. This is followed by attack of halide ion and nucleophile. So initially, hydrogen ion, that is H plus ion, it attacks this triply bonded, one of the triply bonded carbons to produce vinyl cation. This vinyl cation, it combines with the X minus, which is present in the reagent, to form finally alkynyl halide. Alkynyl halide. See this. This is an this from HX, this H plus. With the help of the pi bond electrons, this CC triple bond pi bond electron, one of the pi bond, it abstracts this H plus to form a bond. CH bond, new sigma bond is produced, a pi bond is broken, and this adjacent carbon to the CH bond, this carbon, it suffers with a positive charge because it has only 3 bonds surrounding it. Therefore, it has a positive charge. Thus, it is a carbonium ion or cation. Carbonium ion or cation, that is vinyl carbonium ion is produced or vinyl cation is produced here. This vinyl cation, if this and this are H, then we should say vinyl cation. Okay, vinyl carbonium. So this vinyl carbonium ion, it now combines with the X minus, which is present in the reagent, to form finally here X gets added. Then we will get finally alkynyl halide. Alkynyl double bond is there. That's what it is called, alkynyl. Okay, alkynyl halide is the product produced in this reaction. Okay, let us see the specific example. When hydrogen halide adds to terminal alkyne, the product has the orientation predicted by Markovnikov's rule. So when hydrogen halide is added to terminal alkyne, the product obtained is according to Markovnikov's rule. Yes. So what is Markovnikov's rule? We know. According to Markovnikov's rule, the negative part of the addendum goes to the carbon containing less number of hydrogens. Negative part goes to the carbon containing less number of hydrogens in among the C triple bond C carbons. Okay. So now here we are adding HCl to this molecule, that is propane, CH3 C triple bond CH propane. Okay. When we add HCl to this, from HCl, H is positive part and Cl is negative part. Okay. So the negative part goes to the carbon with the less number of hydrogens. In between these, here only addition takes place. H and Cl go and attack these two carbons only. There only one pi bond breaks and two new sigma bonds are produced. So H goes to which carbon and Cl goes to which carbon, that is more important. So when H goes to this carbon, terminal carbon, then what happens? We will get a plus charge on this carbon. This is secondary carbon. Whereas if H goes to this carbon, middle carbon, then positive charge will be on this carbon, which is a primary carbon. And we know that secondary carbocation is more stable than primary carbocation. Therefore, H has to go to, it has to go to this first carbon so that it becomes CH2 and this becomes plus, then Cl minus goes and attacks this carbon to form the final product. So this is only Marconikov's product. So when hydrogen halide adds to terminal alkyne, the product has the orientation predicted by Marconikov's rule. So according to Marconikov's rule, the positive part of the addendum goes to carbon with more number of hydrogens, or the negative part of the addendum goes to carbon with less number of hydrogens. Therefore, here Cl goes to this carbon which has less number of hydrogens in between these two, which has more number of hydrogens. Therefore, we will get CH3 is CCl double bond CH2. You can see here CH3 CCl double bond CH2. So this is 2-chloropropene. 2-chloropropene is the product obtained here. Okay. So this is about the addition of hydrogen halides to alkynes. Okay. So next, we will continue with the rest of the properties in the next class. Thank you all.